In this video, we're going to look at how to calculate Ka or Kb equilibrium constants. So often when dealing with acid-base equilibria, you're going to be asked to calculate the value of an equilibrium constant, either Ka or Kb, for that particular acid-base reaction. So generally, the first thing we need to do is determine the equilibrium concentrations for the reaction. Of course, we have to have equilibrium concentrations to calculate our equilibrium constants. Then we write the equilibrium expression for that reaction. Finally, we substitute in the equilibrium concentrations into our expression and solve for Ka or Kb. Now remember, Ka or Kb values are associated with weak acids or weak bases in water. Ka or Kb for strong acids or bases are usually too large to measure, so we don't have to calculate those. So to show you how to calculate this, let's look at a sample problem. Here, we're given that the pH of a 0.250 molar hydrofluoric acid solution is 2.036. What are the values of Ka and pKa for hydrofluoric acid? Now, before I show you how to do this, pause the video and see if you can figure out the answer. Okay, so generally, since this is an equilibrium type problem, we want to be able to write the correct equation that describes our equilibrium. So here we have hydrofluoric acid in water. Acids dissociate to lose a proton, and therefore we would end up with H3O plus hydronium ion plus F minus, our conjugate acid and our conjugate base. Next, let's set up an ice table, which will allow us to keep track of our concentrations. We want to keep track of our initial change in concentrations and equilibrium concentrations. Now, here we're given the initial concentration of hydrofluoric acid, so we can plug that in right here. Okay. So we have our initial concentration of hydrofluoric acid. Water is a pure liquid, so we don't have to worry about the concentrations because it remains constant, so I put Na there. Our initial concentrations of hydronium and fluoride are approximately zero. Again, we do have a little bit, but just from the dissociation of water, but essentially it's zero, and the initial concentration of the fluoride ion can be zero. Now, next, we have to appreciate what the pH tells us. What exactly does the pH mean? Well, the pH is an expression of the equilibrium concentration of hydronium ion. Remember that pH is equal to the negative log of H3O plus, and this H3O plus is the equilibrium concentration. It's very important that you appreciate that. So given the pH, we can rearrange that to solve for the hydronium ion concentration, which will give us the hydronium ion concentration at equilibrium. So we just plug in our pH into our expression and solve for hydronium, and we get an equilibrium concentration of hydronium of 9.20 times 10 to the minus 3 molar. And so that value is going to go right in here. So again, it's very important that you have a very good working knowledge of exactly what the pH tells us and how to convert that into a hydronium ion concentration. So now we know the equilibrium concentration of hydronium, but we still need the equilibrium concentration of hydrofluoric acid and the fluoride ion. So we know that our reaction is going to proceed from left to right. Now that's important because we need to determine our changes in concentration. Initially, we had no hydronium or no fluoride ion, so we must go from left to right initially. We use our reaction stoichiometry. For every 1 mole of hydrofluoric acid that dissociates, we're going to form 1 mole of hydronium and 1 mole of fluoride. So we have to pay attention to our stoichiometry. So our hydrofluoric acid concentration is going to decrease minus X, hydronium is going to increase plus X, and fluoride is going to increase plus X. And again, it's a 1-to-1-to-1 stoichiometric relationship because of our balanced chemical equation. So take a look at this. We know what X is because we started out at 0 for hydronium and we formed 9.2 times 10 to the minus 3 molar concentration of hydronium. So our increase, or our X, is going to be equal to 9.2 times 10 to the minus 3. Now again, the relationship between hydronium and fluoride is a 1-to-1. So for every 1 mole of hydrofluoric acid, for every 1 mole of hydronium that's produced, we produce 1 mole of fluoride also, and we lose 1 mole of hydrofluoric acid. So again, we get this from our stoichiometry, and we know what X is. So now we can figure out what our concentration of hydrofluoric acid is. We just have to subtract 9.2 times 10 to the minus 3 from our initial concentration, which we have here. And here we're going to add it to our initial concentration of fluoride, which is 0. So we should have equilibrium concentrations of 0.241 molar and 9.20 times 10 to the minus 3 molar for fluoride. So again, please appreciate how we determined our equilibrium concentrations. That's key. Now we just need to write our equilibrium expression. We know that the Ka is equal to our concentration of products divided by reactants. We don't include water in this. And we have our equilibrium concentration, so we can plug those in and solve for Ka. So we get a Ka value, 3.51 times 10 to the minus 4. Now our question also asked us to calculate pKa, so we just have to take the negative log of our Ka value, and we should get 3.454. Again, to 3 sig figs, the 3 is an exact number, so we have our pKa is 3.454. So let's take a look at another problem. This one deals with Kb, but it's a similar type problem. Codeine is a weak organic base, and we're starting out with a 5.0 times 10 to the minus 3 molar solution of codeine, and it has a pH of 9.95. Calculate both the Kb and pKb for this substance. Again, pause the video and see if you can solve this problem. Okay. So the first thing we want to do is write our balanced chemical equation. Now, I've just written codeine as B. We know it's a base, we're told that. And so I could have written the entire chemical formula, but just for the purposes of being brief here, condensed, so I've wrote B to represent codeine. And codeine is placed in water. Now remember, bases accept a proton. That's the definition of a base. So our base is going to be protonated by the water. The water will be our weak acid. And so we'll end up with Hb plus and OH minus. So did you write your correct equation? Be sure you can do that. Next, let's set up an ice table. Again, here we have B representing codeine, and here we have our equation. Then let's plug in our concentrations. Our initial concentration of codeine was given. Our water is not applicable here since its concentration is constant. Our Hb, our protonated codeine, initial concentration is 0, and hydroxide is approximately 0. Again, there's a very small amount of hydroxide in our water solution, in pure water, but we can neglect that here. So now let's figure out what is our concentration of hydroxide. We can do that using our pH. So that's very important. We know that, as we said before, the pH is equal to negative log of hydronium, and the hydronium can be calculated, as you see here, 10 to the negative pH. So I can use that to calculate my hydronium ion concentration. But again, I want hydroxide, not hydronium, but we do know a relationship between hydroxide and hydronium. The hydroxide ion concentration at equilibrium is equal to Kw divided by hydronium. So we know Kw is a constant. We know our hydronium, we just solved for that. And so here we're able to solve for our equilibrium concentration of hydroxide. We can plug that into our ice table here. Okay. So now that we know our hydroxide ion concentration at equilibrium, we can determine our changes. Again, our reaction is going to proceed from left to right because these concentrations over here on the right are all initially 0. So my base is going to decrease by X, and my conjugate acid and my conjugate base are going to increase by plus X and plus X. Again, everything's a one-to-one stoichiometry. I know what X is because I started at 0 and I ended up with 8.9 times 10 to the minus 5, so that's going to be equal to X. So now, if I know what X is, I can fill in my blanks here. My base concentration is going to decrease from 5.0 times 10 to the minus 3 molar. It's going to decrease by, or subtract from that, 8.9 times 10 to the minus 5. Over here, it's going to be 0 plus 8.9 times 10 to the minus 5. And so we're able to calculate our equilibrium concentrations. Next, we can set up our Kb expression, and we can plug in our equilibrium values and solve for Kb. And we get a Kb value of 1.6 times 10 to the minus 6. Finally, we were asked to calculate pKb. So we have our Kb. pKb is the negative log of our Kb value. So we just take the negative log of 1.6 times 10 to the minus 6, and we get 5.80 as our pKb. So practice some more of these problems where we're asked to solve for Ka or Kb, and be sure you understand how to use the pH or the pOH in order to get your equilibrium concentrations.